Hey guys, it's Charles and welcome to Good Clinical, a podcast and YouTube channel dedicated to showcasing the future of medicine and human health. Today's episode is another in our partnership with Te Titoki Mataora, the MedTech Research Translator. Today's guest is Dr. Vickie Shim. Vicky is a Senior Research Fellow at the Auckland Bioengineering Institute, and her primary research focus is neuromechanics and its application to injury and degenerative diseases. Vicky's primary focus right now with Te Titoki Mataora is the development of an AI-based tool to help project recovery trajectories for individuals who've experienced mild traumatic brain injury. Oof, what a mouthful.
Yeah.
Welcome to the podcast, Vicky.
Thank you for having me.
Man, yeah. When we were talking earlier about the project and your work, I find it incredibly fascinating. It's like the marriage of physics and biology and neuroscience and all these other different disciplines. What do we need to understand about neuromechanics from a very high level, obviously, to understand the line of work you're in?
More widely used term for that would be biomechanics, where people combine the mechanical concept with the biology, mainly human body. Now, neuromechanics is more focused on the brain side of the things, because all human tissue is what we call mechanosensitive, that respond to mechanical stimuli. So neuromechanics specifically looks at how brain tissue respond to external stimuli in terms of a mechanical impact. So the direct application will be something like a brain concussion or brain injury. So that's the area that we're looking at.
So broadly speaking, the brain doesn't respond that well to mechanical impact, does it?
So brain, because the brain tissue is encased in this very hard skull. That's the problem here, because if you get even the very little impact, the brain inside the skull might vibrate a bit, and then it hits the skull very in an unpredictable way. So that's why we would like to avoid even a slight impact to the brain to protect the brain from the damage.
Yeah, so it's not, I mean, if you were to design the perfect encasement for a brain, it wouldn't be a super hard skull, would it? It would be some kind of...
So there must be a reason why the skull is so hard. Yeah, but there are some protective layers between skull and the brain. But if that's that's why some minute movement, like your head movement, heel tilting, that's like that. So in that case, the brain is okay. But if there is like a direct mechanical hit from outside, external stimuli, then the brain might move inside the skull in a way that we don't know what the damage will be like.
Yeah. And so when it oscillates within the brain cavity, so if you say you're in a heavy car accident, you stop suddenly or you hit your head against the wall, your brain keeps moving and then it pushes against your skull and then goes back because it's very fluid, I suppose you could say.
Yeah, that's why when we open up, so this is not a good word, but when we see the inside the brain after the head impact, usually it's the opposite side of the impact location that's more damaged than the area where the brain is impacted, because the brain moves in an action-reaction kind of way that it hits the back of the skull. So that's where the damage occurs.
Right. So potentially if you get hit at the front, which is a different part of the brain, but the back is where the vision is. Yeah. So you get hit here, but actually the damage is at the occipital.
So if you hit here, then you might be this side as well. So that's kind of very. That's why brain is so fascinating. It's one of these. I think a brain can be regarded as the most soft tissue in the body. It's very gel-like, almost like a tofu-like. Yeah. So that's how soft it is. Yeah. And encased inside this very hard skull, of course, there is a layer that protects it from that, so working as a shock-absorbing layer. But still, we have the brain can be damaged from this head impact quite easily. Yeah.
And what's happening when the brain's getting damaged? Are the cells dying, or are the cells losing connection to each other?
So there are many things that can happen. So on a neuron, the brain cells, direct brain cells, where the information transfers. The brain, people found out that if the brain neurons are stretched too much, we call axonal damage. So that affects the way the information transfers within the brain. But it's not just a neuron that gets damaged. There are other neighboring cells around these axons that helps with the blood supplies or other areas. So another area that we looked at was the brain vascular supply, where we looked at the cell called the pericytes, where it layers the brain vasculature, but then once it's damaged, it kind of moves away from the brain vasculature, leaving the brain vasculature more vulnerable.
Oh, okay.
So there are not just the direct impact from the hit, but there is secondary injury as well. So that's a fairly complicated process.
Absolutely, which
Yeah.
kind of raises the question, answers the question why we don't have an answer for a lot of these questions. I mean, before we got rolling, you said that, when it comes to major traumatic brain injury, that's fairly straightforward because you can treat it more straightforwardly. Whereas when it comes to the mild traumatic brain injury, it's more cumulative. It might not be so egregious, you don't need to treat it, but it does have an effect on the brain.
Yeah. So the TBI in general is kind of, you can have it's a spectrum of diseases like many other neuro diseases. So you can have a very severe or moderate TBI, but there is a mild TBI, and almost 80% of all TBI is mild range.
80%?
Almost 80%.
Wow.
Yeah, majority of the TBI are regarded as mild. But so some of them recover naturally by having a natural enough resting period, doing nothing too strange after hit. But some of them, although they follow the usual protocol, they have a longer term effect. So they still have sensitivity to the light, headache, difficulty to sleep, that kind of classic TBI symptoms, even after 3-4 months. So we don't know why some people have this prolonged effect from the MTBI, mild traumatic brain injury, while others naturally recover. So we would like to find out why some people have that.
Yeah, what's going on in the healing process or the cumulative. So 80% is mild TBI. How would you divide the different categories? So mild, moderate, and severe.
Yeah. So that's very gray area too. There is diagnostic scale people use. They have the questionnaires, whether they are conscious, whether they have bleeding. There are certain questionnaires that they have answer, and then depending on how many are yes, then you can be categorized as a severe, moderate, or mild. So that's, but it has been very useful clinically to identify the severe and moderate TBI. But in terms of mild, still we don't know why some have this ongoing symptoms after that. So.
Right, and mild TBI, this could be someone that had a mild concussion or a concussion and had prompt recovery, promptly regained consciousness, or someone that didn't have any loss of consciousness, no concussion, but just repeated head injury or mild.
So that's, so mild has a concussion and there's subconcussive injuries.
Okay.
Yeah, so
under the mild umbrella.
So it's a whole spectrum.
I see.
Yeah.
And just out of curiosity, to get you from that mild to moderate level, is that like a I don't know, how do we define that? Is that
so it's that, and that's where you get to go to ER.
Okay. Yeah. Like, is that bad?
That bad. Yeah. Then
immediate attention
is required.
Okay.
Yeah, because you are now at risk for. Yeah.
Okay. So I mean, those severe ones where you need immediate medical attention, they kind of get the medical attention and the attention, but obviously the mild ones still, there are, long-term implications from repeated head injury, mild TBI. So you in your research, you're looking at implications of this for recovery. Why do some people recover quickly, heal quicker than others, and what's going on? So what's happening at the moment? What have you done previously to lead up to the current projects that's supporting these investigations?
So since 2021, we've been studying brains of high school rugby players. So we are working with I am also affiliated with the MedTech Research Institute down in Gisborne. So what we do is we work with the Gisborne Boys High School. So what we do is that we follow their brain change over a rugby season. So what we do is that we give them what we call instrumented mouth guard. That goes with your mouth, and then it measures the head impact that they receive during games and practices throughout the season. And then at the same time, what we do is that we do the brain scan at MedTech with their MRI scanner there at preseason, mid-season, and post-season. That way we can track the brain changes over the season and correlate that with the amount of head impact that they received. So that's what we've been doing since 2021. And this year, we expanded our collaboration with Otago University. Now we are also working with girls in the, I think it's Otago Girls High School. Sorry. Yeah, the girls. And then, so we're now doing the same thing with the girls down in Dunedin. And so we do the same. We give them the mouth guard and then measure their brain changes over time.
Wow.
So far, I think we have followed about 70, 80 rugby players, and then about 30, 40 controls, so more than 100 subjects so far.
Amazing.
Yeah.
And the controls, those are non-contact sport
So the
players.
controls have to be compatible with the rugby course, so the age-matched, non-contact sports playing athletes.
Right, so they might play...
Like the rowers or track and fields.
Yeah, not soccer, because there could be some...
Not soccer, not even baseball, I think. But
oh, really? Oh, yeah, I suppose they run into each other periodically, don't they?
Yeah.
Okay, so the mouth guard, does that have like an accelerometer or something in it that
so
measures the change in the head direction?
Yeah,
or?
so it measures two ways that head respond. One is the linear, that is the linear head movement, and then rotational head movement. And that they can measure it in terms of acceleration, because that's what causes damage. So we measure the linear and angular accelerations that player received throughout the season from the games and practices.
Yeah, and are they given like a cumulative score, or is it a game score or a practice score of their acceleration?
At the end of each games or sessions, the coach will receive statistics as to who received more and stuff like that. But what we do is that we collect all the data, and then we identify those who have received more head impacts than others. Because some players, because we usually work with the first 15, but sometimes we also have second 15. So the number of times that they go into the fields vary from player to player. So we can see that which players played more and they received more head impacts.
Right.
And then we can correlate that amount of head impact with their actual MRI scans that they have 3 times of the season.
So I suppose, I mean, you've got your backs in a rugby versus the forwards. The forwards are taking a lot more hits than the backs are.
So if you just look at the head impact, you can probably predict, this guy's a forward, this guy's a back, something like that.
Of course,
because they're quite different from player to player.
Yeah. Oh, winger, you only got a couple hits. Lucky him.
Yeah.
So you've got the data on the hits throughout the entire game playing season, and you're correlating that with the brain changes on the MRI pre, mid, and post season. What changes are you looking for specifically on that MRI?
So MRI is, we can look at various things with MRI. One is brain structural change. So brain has gray matter and the white matter. And the white matter is the area where information travels from different parts of the brain to another part of brain. Now, we call it the white matter fiber tract. That's kind of what we call information highway, where information travels. And integrity of that highway or white matter fiber tract can change over time from external factors, such as head impact. And that's what we have observed from our latest study, where we saw the rugby players' brain did change over a season when compared to the non-contact sports playing athletes. The bimetal fiber tracks the structure, microstructure has changed. It remains to be seen whether that will lead to functional deficit, or is it maybe it's from contact sports playing or this maneuvering that might have affected brain change, because these brains are what we call developing brain. So the normal development might have caused this. On top of this additional sports activities. So it remains to be seen, but at least we can confirm that the when compared to the non-contact sports playing athletes, the rugby player's brain changed after one season.
Wow.
So we still don't know whether the brain will recover over this break period. So it remains to be seen, but at least that's what we are reporting.
Yeah. So will you do like a next season? So if they come back for the next season, you do like they haven't played for the last 3 months or 4 months, and have a look at if their brains have recovered.
Yeah, so we can look at that. So we have a few boys, very grateful for their volunteering for this study, who volunteered to participate in this MRI study year after year. So we are very looking forward to analyzing that data set to see whether the resting was enough. Or these changes are not significant enough to cause any functional changes either.
So I suppose to find out if there's any long-term implications, it would have to be like quite a lengthy longitudinal study over time.
So every study has a limitation. So the reason that we picked the young boys is because those adult players have been playing for decades. So what we wanted to see was more early stage of the brain. But then it's also, there's another additional factor is that the brain naturally changes because they're still growing. So we have to take that into account. So that's another thing that we need to do.
Yeah. I suppose it'd be good to see in other contact-related sports as well if you have the same findings.
So we would love to work with other sports, especially netball. Because netball, surprisingly, has a lot of... because head impact is not only from the direct hit to the head. Other hit to the shoulders or any upper body jolt can lead to head impact. So netball is another one that we would love to see, because the neck musculature, we would like to see how it plays a part. Because girls have worse outcome from the concussion than boys. We don't know yet why.
Is that right?
Yeah, a lot of speculations, like it's the weaker neck musculature that might give a less stability. We don't know yet.
Is it like worse outcomes from the same level of force or acceleration type thing, or is it just across the board?
So it's across the board, because we cannot completely match the same impact unless it's animal experiments. So, but girls have worse outcome in general than boys, the men or women as well. So that's another area that we would like to see.
So I suppose in that instance, when you're following these boys in the future, these girls playing rugby throughout the season, you're like you said, cumulatively pulling out how much head. What did you call it before? The acceleration effects?
Head acceleration events.
Events. Sorry, not effects. Throughout the season, and correlating that with the MRI, and that's in instances where there's no loss of consciousness. So it's not that's a more subconcussive effects. What about the concussive side of things?
So those who experience concussion, clinically diagnosed concussion, we pull them out. Fortunately, we don't have that many. It's about 3-4 per season, so it's fairly normal rate for junior rugby games. So 3-4 or maximum 7-8 per season. So we pull them out because their brain has been impacted a bit more severely than subconcussive impacts, we put them through more rigorous MRI scanning protocol. So rather than pre, mid, post, we pull them out and we scan their brain within 24 to 48 hours once. And then we scan them again within a week, and 3 weeks, and then 8 weeks. That way we can see how the brain, the recovery trajectories of the brain. And then we can identify how long it takes for the brain to recover.
Right.
And what we want to do is that we correlate that time frame or recovery trajectory with the initial hit that caused the concussion.
Yes.
And that way, that's how we would like to progress with this study. Yeah.
I see. And then in doing so, for of someone who's playing rugby, they have a concussive event, but they've got the mouth guard with the accelerometer in it, and that can help predict how long it's going to take them, how much time they should be not playing rugby, for example.
So currently, I think that's the normal stand-down period is about 23 days.
Is that all?
Yeah, that's all.
For concussive?
For concussive, for those who have a concussion.
Yeah.
For junior rugby players, we may need longer, or we don't know. And those who did not experience concussion, but maybe close to concussion, or they feel not good, then we can also use this method to predict, or what we call clinical support tool, where we can provide suggestions like your hit magnitude was this much, and your brain is likely to have changed about that much, so you need this much time stand down period. So
right.
That's what we trying to do with this TTM Rep2 funding.
Yeah, and that's so cool, because if you don't know, then you have no reason to enforce some kind of stand down. Is 23 days too long? Is 23 days far too short?
Yeah.
When should we apply any kind of cutoff?
Yeah.
So is the 23 days, is that more or less arbitrary /
No, I think the World Rugby did some research. They do quite a bit of research in this area. So they have done some research to come up with this generic guidelines. So like that covers everyone. But as you just said, it might be too long for some. It might be too short for some. So you would like to give some more objective, quantitative diagnosis for concussion. Yeah, personalized way.
Yeah, I mean, we're in the age of personalization, right?
Yeah.
Like not one size fits all.
Yeah.
I had another guest who's part of the TTM partnership that we have, and they're designing bras for unique. I'm sure you know Zuzu. I think I've seen, personalized. To fit someone's anatomy and preferences. I mean, we're in that, and then we've got personalized medicine, like need personalized prognoses for concussion. It just makes sense. Yeah. So in terms of the RAP project, so that's the AI tool to help inform the predictive recovery. The application of that wouldn't just be for rugby injuries or rugby concussions, right?
So our ultimate goal is to make this as a sort of like a handheld device-based tool, because we understand that not everyone will have this head impact information. Not everyone will be wearing the mouth guard when they do a mountain biking, for example. So, but if we know the person's overall body weight and then the activity that they were engaging at the time of incident, and then we can recalculate or back calculate, we can estimate amount of head impact they might have received from the fall or whatever incident that they experienced. And then from that, we can predict what kind of recovery regime that they need.
Yeah.
So it's not just the stand-down period, but like because there are some protocols for the concussion treatment. So we can sort of like personalize what would be the best for you, and provide suggestions for the recovery. So that's sort of like a longer term goal. But for now, the short term goal is to have this as a handheld device-based tool for contact sports players or combat soldiers, those who are known to be exposed to the repetitive head injuries.
Yeah.
because for these are the most at-risk group.
Yes.
The problem with the head impact is that once is okay most of the time, but if you get the second one too early, we call it second hit syndrome. Can be fatal.
Really?
Yeah, if it comes too early. There were instances. There was a very famous story in Canada where a girl was playing rugby. She had a concussion. It wasn't even a concussion. It's just hit a little bit severe, and then she had it second one too early, and that led to her death. So that becomes a very it was a very headline news at the time.
Yeah. Do you know what the interval was between the two?
Few days.
Right.
Yeah, so she felt not well after the first hit, but then the team sports, she had to play for her team members.
Right.
And then the second hit, which was not even a serious hit at all, then that caused this kind of very serious incident. So that's what we want to prevent to start with. That's our first aim. Mm-hmm. And then because those players have those mouse guard information, so we can give them more objective, quantitative information about their possible recovery trajectories.
Yeah.
Yeah.
Yeah. And when you say handheld, do you mean like actually?
Yeah, the phone.
Yeah.
Yeah, because at the moment the mouse guard is also connected to the handheld devices.
Oh,
it's
I see.
Where the receiver receives and transmits the information.
Yeah. So the
sense.
sensors will be in the mouth guard.
Yeah.
And you could retrieve the data on your phone or whatever other handheld device to give you, stand on period 5 days, and you need this kind of recovery protocol.
Yeah, it's a real time thing.
That's so cool.
That's our aim. Yeah.
Yeah. Yeah. So of course, I mean, you got to start with the most where the biggest need is, and that's with the rugby players, right? But then there are other avenues you could take it. So for soldiers, is that explosives that they're around that causes the
explosives
head?
And then the trainings that they go through, because during their training, when they experience those explosive the training, because they do that very regularly. So not just actually those who participate in the battlefield experience, but from the trainings, the regular trainings that the soldiers are exposed to, this repetitive, a little bit different from head impact because there's no direct impact to the head, but the impact comes in kind of waves in that way. So we call it blast injury. So blast injury. So that's another major area that people are interested in to prevent the soldiers from getting those kind of repetitive, unnecessary head impact.
Yeah. And why should we prevent the repetitive nature of this? What are the downstream implications of too much exposure? So you said one, probably okay, brain will recover over time. What's specific about the repetition?
Yeah. So a lot of people are now aware of this cases of rugby players or soccer players who experience this what we call traumatic chronic encephalopathy. That's you from this repetitive head impact throughout your lifetime, your career basically. And then those people are often at risk for developing early neurodegenerative symptoms such as Alzheimer's or Parkinson's. That's where, and unfortunately, those symptoms can only be diagnosed post-mortem. So there is no way to diagnose that yet. So best way is to prevent, like many other things.
Yeah.
We don't want our kids, players, or soldiers to go through that and then experience symptoms of Alzheimer's or other neurodegenerative symptoms in their 30s or early 40s. That's too early. And
so the symptoms of CTE, so they're Alzheimer's. They can be Alzheimer's-like. It's not Alzheimer's, and it's not Parkinson's, but it's Parkinson's-like symptoms based on whatever part of the brain has been kind of affected. And but I was talking with another one, in Parkinson's in particular, that you only start to get symptoms once you've lost 60 to 70% of the cells of the substantia nigra, which is the cells. So I imagine if you've got chronic traumatic encephalopathy, it's not until you've lost a lot of brain tissue or there's a lot of damage has been caused before you start getting the symptoms, and then it's too late, right?
Yeah. So the fact that those who play contact sports or soldiers, combat soldiers, experience that so early in their life means this repetitive head impact might speed up that process, speed up that brain degenerative changes. So we don't know yet because it's very hard to study with other factors influencing the brain changes. So that's why we study with the high school boys, so that we can minimize that other factors influencing the brain. But the hope is that we can find out this kind of objective way of diagnosis and prognosis of MTBI, so that we can prevent that from happening as early as possible. Yeah,
absolutely. I mean, what I love about these kind of things is that you've got the objective data that can really inform you, as opposed to some blanket statement that would apply. I think it's fantastic. I mean, I always find in my life, I like to say to my wife that, I know what I should be doing, but I kind of don't do it. But, when it comes to like eating well and exercising, all these things that like you're supposed to do to keep yourself healthy and prevent. But in something like this, like it should be pretty clear cut. You had a big hit. This would otherwise cause, some kind of damage. You need to recover for this period of time. Yeah, I think that kind of objective data is so helpful.
Yeah.
What and as part of the TTM framework, what has been like your most enjoyable part of the process working with TTM? And this is your second rapid
so
research acceleration program.
Yes, we are extremely grateful for TTM for supporting us second time. They supported our last data collection. So thanks to their support, I think our data set is definitely the largest MRI-based MTBI data set that we collected so far.
Wow.
And because we're continuing with the TTM support, it may be one of the largest in the world, because the problem with this data collection is, it is very expensive. MRI is very expensive. But more importantly, we need the community support. They have to volunteer to participate in the study. So the most rewarding thing that we have so far is the community engagement. So we get to talk to the players, the parents, the coaches, and the school, and build up this personal relationship with them, share the findings with them. They love looking at their MRI scans afterwards. And some of them, we're so grateful that they continue to come back and volunteer. So this kind of engagement with the community, and with the hope that we can, in the near future, we can bring out some nice product so that they can use them themselves. So this kind of most rewarding part of this project, that we have this engagement with the various communities.
Yeah, and I'm sure, once you do have the product, they'll be the first ones to use it and benefit from it.
Yeah.
How fantastic. Well, Vicky, this has been a great, quick little conversation. Thanks so much.
Thank
you. If people want to find out more about what you are doing in your research, where can they go?
They can contact me directly. My email, v.shim@auckland.ac.nz, or they can also contact people at MATAI, because they are the one who were collecting the data. So matai.org.nz. So, or just ABI. I'm at the ABI all the time. So you can contact us via ABI as well.
Excellent.
Yeah.
Well, thank you so much.
Thank you.